This assessment is asking us to rationalize why the carbonyl oxygen is the oxygen that attacks aluminum when we use dival as a reagent. Oxygen in this mechanism is acting as a nucleophile when it attacks aluminum, so another way of asking this question is why is the carbonyl oxygen more nucleophilic than the ester oxygen? To answer that question, let's look at the resonance contributors for an ester. One resonance contributor we can draw is to break the carbonyl pi bond push electrons onto oxygen. That gives us a resonance contributor that will have a negative charge on oxygen and a positive charge on carbon. Another resonance contributor would be to use the lone pair of electrons from oxygen to form a new carbon-oxygen double bond. That will still keep a negative charge on the oxygen on top, but now the oxygen of the ester has a positive charge. These are the major resonance contributors for this particular ester. Looking at these resonance contributors, we see that the oxygen of the carbonyl ends up with a partial negative charge in the resonance hybrid, and the oxygen of the ester ends up with a partial positive charge in the resonance hybrid. A negative charge on the carbonyl oxygen means that that oxygen has more electron density overall. Because it has more electron density, that means it is more reactive and more nucleophilic, and it is the reason that the carbonyl oxygen is the oxygen that preferentially reacts with aluminum in this mechanism.